Hello, everyone. Let's finish off what's left over in section 4.4. In our last lecture, I believe that was lecture number 7, we began the idea of spanning sets and linear independence. So I just want to recall some of the concepts, some of the topics that we went through, and then we'll carry on with the rest of the section. So first, we talked about what we mean by linear combination of vectors in a vector space. So for instance, let's say we have a finite number of vectors. These are u's, u1, u2, and u sub k. And the linear combination is simply the sum of those, and we are allowing for C to be a coefficient scalar multiple of each of those. So we have a scalar multiple of individual vectors and their sum. And that's what the linear combination is. So in this example that you're seeing from the author, so in this set S, there are 3 vectors in R3. So for instance, the linear combination 3v2 plus v3, those add up to v1. Therefore, it is possible to write v1 as a linear combination of 2 other vectors. And well, let's see. Let's take a look at the next idea. We did do our own examples where we had to find linear combinations. So again, I just want to pick up, this is just a brief review of what we've already done, the work we've done. If you need more review, please watch the previous lecture, lecture number 7, I believe. We did define spanning sets. So remember, this vector space V is a space where it's got a whole bunch of vectors in it, right? It's got vectors in it. So if you look at a subset of those, V1 through Vk, then we call that a spanning set. So a spanning set is simply a subset of those vectors in the vector space. Okay. Now, but if every vector in V could be written as a linear combination of these, then we say that set S spans V. Okay, so that was a definition of a set of vector spaces and what we mean by span of S. So again, if the vectors, the subset that you choose from the vector space, if the linear combination of those cover every vector in V, then we say the set spans V. So for instance, here we have a good example. Let's say you have this set that's made up of vector 1, 0, 0, 0, 1, 0, 0, 0, 1 in R3. Now, every vector in 3D, you can create your own vectors, your own coordinates, if you will. Everything you create will be a constant multiple of one of these vectors, and of course, the linear combination means their sum. So sum of a scalar multiple of each of these vectors. So for example, if I have my vector is 3, 4, 5, well, that would be 3 times u1, right? 4 times u2 and 5 times u3. So every vector in R3 is made up of these 3. So we say that this set spans vector space R3. All right, and then the definition of a spanning set. Again, we went through this already. So a spanning set is simply a set of vectors. That's what it is, that it spans the vector space. So that means you can write every vector again in V using the linear combination of the vectors in the spanning set. And there you go. That's what that is. Okay. And when the span of S is equal to V, that means that every vector in V is covered by it. Then we say V is spanned by vectors in S, or simply S spans V. Okay, so it's a lot of terminologies here. Okay, and so now this is new material what we're about to start with. So let's take a look at this theorem, first of all, without the proof. Theorem 4.7 tells us that the span of S, remember, is a subset of vectors that are in V. The span of S forms a subspace of V. And so that's what this theorem says. So suppose we have span of S, that means a set of vectors in V. Then the theorem says that this is a subset. Okay, now this is interesting. The moreover part, it says the span S is the smallest subspace that contains S. In a sense, every other subspaces must contain an S. In other words, the span of S is unique. So if you come up with other subspaces of S, right, then every one of those must be contained in S. That means any other linear combination of vectors in V that you create will be part of this. Those themselves could be written as a linear combination of vectors in S, span S. Okay, so again, that implies the uniqueness. So it is the smallest, and they also call this the minimal span. That's what it's called. It's called the minimal span. Okay. And what do we see? What do I mean by minimal is that talking about the smallest number of vectors needed to generate the entire vector space V. It's the minimum in that sense, the smallest number of vectors. So, for example, I can use only three vectors to represent a vector space instead of four vectors, something like that. Okay. Now, in order to prove this, remember we have to show what you call it. We have to show three things. We have to show the set is non-empty. We have to show that the set is closed under operation addition and scalar multiplication. That's for any subspace, remember? So we need to show closure. First, the zero. The set S is non-empty. Okay, non-empty. That means zero is in the set. And that is done because the subspace, remember these vectors in S, the span S, the vectors in there they belong from vector space V. And vector space V, to be a vector space, has the zero vector in it. So in a way, that is directly inherited from the vector space. So we know the set S is non-empty, means it has at least a zero vector in it. Now, if you choose any two vectors in general, U and V, well, you can see the sum, U plus V, will be in the set. And here's how you show it. So you be able to combine the coefficient on V1 from one set with another set. That's what this is. And so on and so forth. So it's closed under addition and closed under scalar multiplication. When you multiply these coefficients, C1 and D1, well, actually, this is interesting. For scalar multiplication, okay, I see. I was going to say this doesn't look right, but you're looking at a constant multiple. You're looking at constant multiple of U. Okay, this is just one of the vectors. You can use V if you like. So it's going to be C for the constant, multiple of, if you choose to, D sub 1, if you go with V. So as long as you can show that one of these is closed under scalar multiplication, that suffices. So both of those, both of those are in there. Now let's see. Oh, to show that this is the smallest is a C exercise 55. Let me take a look at this. I'm going to pause this for a moment to see if I need to do that for you, or you can kind of do it on your own. Hold on. Okay, so let's actually prove this. I looked at exercise 55 and I copied it onto my notepad. And so let me change my share here to my notepad. Just a moment. Let me change my share to my notepad. All right. So here it is. In exercise 55, again, the question reads, prove span S is the smallest subspace of V. So here's how I worked this one. Well, because we want to show uniqueness here. Oh, I'm sorry, not uniqueness. Sorry. Although it is unique, but we want to show that it's minimal or smallest, right? So I'm going to let W be an arbitrary subspace here. Okay, so it's another word subspace besides S. Okay, so this is any subspace of V such that the S, span S, that we're talking about, such that the vectors in S are also subset in, they belong to W, to this other arbitrary subspace. Okay, now, because W is a subspace, remember, I arbitrarily chose a subspace of vector space V. So because W itself is a subspace, that means it's inherited all of those properties that's unique to vector spaces. Remember, there was 10 of them we talked about. 5 had to do with addition, 5 with scalar multiplication. Those 10, it inherits 8 of those 10s. And in addition, because it is a subspace of V, it inherits closure under addition and scalar multiplication. Okay, because I chose a subspace. Now, and therefore, because of the scalar multiplication, just that part of it, that means I can write the vectors in S, the constant scalar multiple vectors S, in any form that I want, and those will also be elements in the subspace W, right? And that has to do because S W contains S. So any constant multiple of that is going to be also in W. So therefore, every element of a span S is also in W. So that means the span S, if every element is in W of S, then that makes it a proper subset, right? So span S is a proper subset of W, and that's what this notation is. It's a proper subset of W. And because W was arbitrarily again selected, it shows that span S is indeed contained in every such space, right? So any other subspace that you choose, uh, span S is going to belong to it, okay? So span S, that makes it the smallest subspace of vector space V containing S. Okay, so that's the proof for those that were interested in knowing the proof. Now, let me go back, change my share, and we go back to the page of the book here. Let's see. Hold on. Okay, so I'm changing my share to the page of the book. Okay, so let's continue on now. Now, one thing I wanted to mention, by the way, here is that if two sets span the same subspace, so suppose I have set 1, set 2, they span the same subspace, then span S1, S2, those two are not unique. If they span the same, not different, but same subspace. So in that sense, it's not unique. And what I mean by that is that the span of S1, let's say, will be a subset of S2, and the span S2 would be another proper subset of the span S1, which in effect means they're equal, they're the same span, okay? Which again solidifies the concept of uniqueness of a span. So if there are two sets that span the same subspace, they cannot be different. It has to be the same. Now, if span of one set is different from the span of another set, then that means they span different subspaces, right? Because the span is unique. So two spans cannot span the same subspace. And if you have two spans that are different, that means they span different subspaces. Okay. So if two sets span different subspaces, then that means some vectors in one span cannot be written as a linear combination of vectors in the other span if they span different subspaces. Okay. Now, we mentioned span S is unique for the same subspace. However, one thing that's not unique would be, and we talked about this later on, we will, is the basis. The basis of a span is not necessarily unique. And it has to do with what do you mean by basis, right? So we still have to get there. But the idea is that different sets of basis vectors can span same space. Anyway, we'll talk about basis later. Now, let me give you an example of what I said about the spans. Okay, so I'm gonna switch to again my notebook here, and let's check out an example here. So I'm gonna change my share to my camera. All right. So here, I have, that's just an example. So I have two sets, set A, set B, simple. A vector in one, a vector in the other. Now, span of A is going to be all vectors that are scalar multiples of 1, 2. Okay. And once you do that, equivalent to what I have here. Okay, so that's A, that's B. The span of A means all the vectors that are in here. Well, all the vectors that are in 1, 2 are constant multiples of it, where C is a real number. So that means the ordered pair xy, y is twice x, right? X comma y is twice x. So therefore, y equal 2x would be another way to rewrite this set. Span B, I made it to be 2, 4, and you can clearly see 2, 4, I doubled up on these two. So what is the span of B? Well, the span of B is the set of all vectors that are constant multiples of 2, 4. So, and where C is a real number. And you can see this one, because you have 2x equals, well, y is twice x, right? So if you have y would be 2x, right? And y is twice that. So y is equal to 2x. And if you notice, these are really the same equations, right? So both spans here describe the same set of vectors. And if you recall the equation y equal mx, it's a line through the origin. Okay. Therefore, span A equals span B. That's what I was saying, the uniqueness of span. If they span the same vector space, this is the vector space here. Two different spans, they span the same vector space, so these two are equal. One is a constant multiple of the other. So that means all the vectors in A could be written as constant multiple of the scalar multiple. Constant multiple is scalar multiple of vector B and vice versa. And I have that written down for you. So every vector in the span A, and equivalently, likewise, every vector in span B could be written as a linear combination of vectors in the other set. Now, here I made up another example. For this example, so you have a simple set. Set A has a vector 1, 0, B has 0, 1. Again, span of A would be all scalar multiples of this one. And this actually forms the x-axis, right? Because you have constant multiple of x, and y is always 0. I'll give you the equivalent to this. There you go, right in here. So this expression is equivalent to that. See, that's y equals 0, which is the x-axis. Span B is all the ordered pairs, all the vectors in the form 0 and a constant. Well, that's the description of the y-axis. That means x0, right? x0. Notice this equation doesn't depend on y, so y could be any arbitrary number. In this one, y is 0, so that means x is free to be any value. So in this one, neither span contains the other, right? None of the vectors here are in here. Even 0, 0 is not on the right because you have 0, 1 here, you have 1, 0, so you can't have. Well, I'm so sorry. No, 0, 0 is there. 0, 0 is there because when C is 0, what do we get? We get 0, 0. When C is 0 here, we get 0, and 0 times 1 is 0. Which gives you that, remember we talked about the trivial subset. It gives you 0, 0. We want, or not trivial, but improper subset. We want proper subsets, so that means not just 0, 0. Okay, now the two of these vectors together, these two, span A, span B, combined, the union actually spans the entire two-dimensional plane. It spans R2. So all the vectors in XY could be written as a linear combination of these two vectors, these two spans. Okay, so again, just wanted to give you an example of that. Now, now let's continue on. So I'm going to switch once again. Let me change my share back to the book. And let's continue on. Now, the next idea here is the linear dependence and independence. So for this one, suppose we have a set of vectors from the vector space V. Okay, so we have a finite set of vectors here. If the linear combination of these equal to 0, the 0 vector, if this linear combination, this is an equation actually, right? It really is, forms a system of equations. If the system of equation here, which is a homogeneous system, right, because they have 0, if that homogeneous system has only trivial solution, that means all the C's must be 0. There's no other way this works. Then in that case, we say the system, if it has only trivial solutions, the system is independent. Okay. Now, if there are non-trivial solutions, then we say that the system is linearly dependent. Okay, this vector space V, these equations will be linearly dependent. So again, trivial solution means the only way this can be 0, the system can be 0, is when every constant is 0, scalar is 0. Then in that case, the system is, the set S, the set of vectors are linearly independent. And what that means is that you cannot write one as a combination of the other. One vector as a linear combination of the others. Okay. Now, and that he explains this here. If the system has trivial solution, linearly independent, and if it has non-trivial solutions, non-trivial, then it's linearly dependent. Okay. Now, non-trivial solutions, that mean one vector could be written as a linear combination of the others. Okay. And this is the definition of that. So, let me give you an example of this. So I'm going to again switch my share to my notepad. So let's take a look at this one example. Okay. In this example, we want to determine, so we're in section 4.4, and this is example for linear independence. So here's a question. We want to determine whether, let's say my vectors are V1, let me make him to be 1, negative 2, 3. And the vector v2, this other vector, these are just random numbers I'm choosing. v2 and v3. Let this one be just 3, 2, 1. There you go. So I have three vectors here from R3. Okay. So we want to determine whether these vectors are linearly independent in R3. Okay, so that's what we want to determine. Now, if they are, then that means, let's see. Oops, I don't know what happened here. Sorry, folks. I don't know what happened. This thing goes crazy every now and then. Okay. So we want to know if these vectors form a set of linearly independent vectors in R3. Well, if they do, then remember the equation, scalar multiple of 1, scalar multiple of V2, and scalar multiple of V3 equals 0. That equation has only trivial solution, okay, if they are independent. Now, let's actually do this. So C1 V1 here, C1 V1, that means C1 times 1, negative 2, 3, right? That's vector V1. Plus C2, that would be times 5, 6, negative 1, and plus C3 times 3, 2, 1. This should equal to the 0 vector in 3. In R3, the 0 vector has all components 0, all three of them. Now, from this, we're going to get a system of three equations, three unknowns, right? So, for instance, C1 plus 5C2 plus 3C3. All the components, first components of the vectors should be 0, equal to this first 0. That would be the x component of the vector. 0, the first component. And likewise, negative 2C1 plus 6C2 and plus 2C3. What did I do? So sorry. C3. These should be C3s. Okay, both of these are C3s. This one and this one. Equals 0. And then the last one is going to be 3C1 minus C2 plus C3 equals 0. So I have a system of three equations, three unknowns. Now, a couple of ways you can determine whether the system has non-trivial solution. First, so here's method one. You're going to do Gauss-Jordan, right? We're going to go to the reducer or echelon form. So the Gauss-Jordan for this, and I did use Symbolab to reduce it, became 1, 0, 1 half, 0, 1, 1 half. You can again use your TI calculators or any calculators, or simply use what I use, the Symbolab. Okay, so this is the Gauss-Jordan form of this. Now, notice we have a row of zeros here, right? A row of zeros. So that means I can let my free variable be C3. C3, I'm going to let this, and here's why. Remember the augmented matrix, because this is a homogeneous system. So here's going to be 0, 0, 0. So if you go to Symbolab, feel free to put exactly this system. I just left the zeros out here. So there's actually, if you will, the augmented matrix here is going to be 0, 0, 0, like that. Okay. And therefore, I'm going to let C3 be my free variable. So if I let C3 be t, then this is the coefficient on C3. And from this, C2 right here, 1 C2 plus half C3. C2 is equal to negative 1 half C3, which is really negative 1 half T. That's my, again, free variable is C3. And what is C1? Well, C1, up here, first equation. C1, again, is move half C3 to the other side, becomes negative 1 half T. negative 1 half C3. So that means I can write this as factor the T out from C1, C2, C3. I get negative a half, and 0. And there you go. So the only solution is not a trivial solution. This shows the system has infinitely many solutions, right? So the system has non-trivial solutions. And if it has non-trivial solutions, what is the implication of that? That means the system is linearly dependent, right? So system is independent. Okay. Therefore, we can answer the question. But these three vectors are linearly independent in R3. That means you cannot write one as a linear combination of the other one. Okay, so that's one method. Method one, using Gauss-Jordan and go to the parametric form of the solutions. The other way we can do this is actually use the determinant. That would be another way to do it. So for my determinant, I'm going to let matrix A be the matrix of coefficients 1, negative 2, 3. And the second one is 5, 6, negative 1, and 3, 2, 1. Okay, so that's my coefficients, right, coming from the matrix directly above. We don't want 0, 0, zeros. And this time, find the determinant of this matrix. The determinant of A, this matrix, ends up being 0. Okay. Now, again, you can use however method or go to software to do it. One thing, by the way, you can see from the Gauss-Jordan, because remember, this is an equivalent system to that one. So look at the last row of zeros. Isn't the determinant of this matrix 0 based on the last row? Because if you do a cofactor expansion by cofactors, then you get 0 times minor of 0, 0 minor of that, 0 minor of that, and the sum of those will give you 0. So anyway, the determinant turns out to be 0 however you do it. So if the determinant is 0, that means system has either no solution or infinitely, right? This means system has either no solution or infinitely many, right? Infinite solution. That's what the determinant would imply, right? 0. In terms of the matrix, that means the matrix is singular, right? That means A is singular. And remember, the consequence of singular matrix is that there is no inverse, right? No inverse exists. So all of these kind of tying together. And we talked about these. A matrix is invertible, means a whole bunch of other stuff. We did that earlier in chapters, near the end of chapter 3, when we talked about determinants. Okay, now the fact that determinant is 0, then this has no solution or infinite solution, right? Well, we know this linear combination has trivial solution, right? So we're going to opt with the infinitely many solutions here, okay? Therefore, we can say from this that the system has, so here we can say system has infinite solution. Okay, the no solution doesn't apply here, folks, because we know the trivial solution works, right? So only for a homogeneous system, I can establish what I just did, because this is a homogeneous system. So it does have a solution. So we just got, because remember, this is one or the other. You just need to investigate, right? So in the case of a homogeneous system, the no solution is ruled out. We go with infinite solution. Therefore, if it has infinite solution, again, that means system is dependent. Independent is independent. That's what that would imply. Okay, so there we have an example of this independence thing. Now, let's take a look at another example. This other example we're going to look at. So for this example now, let's say we want to show this one. We want to show the polynomial in the form 1x squared dot 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 x to the n. This polynomial space form linearly independent set in Pn. Remember, set P for polynomial, P sub n means nth degree polynomials. Okay. So for this one, let's say P sub 0 is going to be 1, and then P sub 1 is going to be x. I'm showing each component as component of a vector, just so it'll match. It will match something like this. Okay. That's P1x. The second polynomial vector would be a vector of all polynomials in the form x squared, and the nth would be in the form x to the nth. Okay, so as a vector now, I can write a p sub 0 plus, let's go a0 to be consistent, and then a1 p1 plus dot 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 plus an pn, and then set it equal to 0. So you can kind of see now why I wrote these as vectors. So this again looks like the general vector form that we talked about when we defined a linear combination. Now, the scalar form of this, if you will, is going to look like this, because this vector is 1. So it's a sub 0 plus a1x plus a2x squared plus dot 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 plus a sub nx to the n equals 0. Scalar 0, not vector 0. Okay. Now, so this one, by the way, we know that this polynomial from algebra, we know that nth degree polynomial have at most n distinct roots. So let me just say from algebra, we know that. From algebra, we know that Pn has at most n distinct roots, right? N distinct roots because it's nth degree. So what would this imply? Well, that means each coefficient here must be 0. That's the only way this can be 0. If one of these coefficients, these are real coefficients, right? If one of them is non-zero, then this will not add to 0. So I'm going to write that. Thus, let's say, I'm going to say each coefficient must be 0. True. Otherwise, it won't equal to 0. True. All right. Again, if that doesn't happen, the left side would be non-zero polynomial. And then, let me say, otherwise, the left side of 0 would be non-zero. Okay. A non-zero polynomial with infinitely many roots. Infinitely many roots. Okay. Therefore, this has only trivial solution. It has only trivial solution. Okay. So that means this, if it has only trivial solution, then it's linearly independent. So independent. Therefore, the set is a linearly independent set. Okay. All right. And now to clarify this for you, I know some of you say, well, I didn't quite get this part, right? So let me give you an example of what I meant there. So this is to clarify my last statement here. So let's say I'm going to make up something, an example. So suppose, let's say my P1 means my first degree polynomial. I'm going to go 1 minus x. Okay. And if this doesn't equal to 0, if this doesn't equal to 0, that means I can write 1 minus x plus another term and make it a squared term. There you go. Then this should equal to 0. See, if 1 minus x doesn't equal 0, that means I can add something to it, becomes 0. So for example, 5 doesn't equal 0, right? Couldn't I add -5? Now it's 0. So if something doesn't equal to 0, let's say y plus 2 equal doesn't equal 0. How about 5? Okay. Wouldn't I be able to add something to both sides that will make it equal to 0? In this case, let's say, I don't know, how about y be negative -7? -7. So here I have y minus 5 equals, oops, no, I didn't want to do that, sorry. How about -5? Yeah, -5. There you go, you get 0. So I added something to both sides and made this 0. Whatever happens to this side, -5 plus 2 is 3. There you go. The key is this, that we can make it equal to 0. So that's what I'm doing here. I'm going to add something in the form ax squared equal to 0, right? Now, what does this ax squared will look like? Well, for this to be 0, shouldn't ax squared be opposite of that, so they add to 0? So for my ax squared, then my ax squared has to be, what, really x minus 1? So that is opposite of that to make it 0. Okay, well, that means ax squared minus x plus 1 equals 0, right? Okay, and how about, so this would work, right? Clearly, if I let ax squared be x minus 1. Now, what if I let another form be 1 minus x plus bx cubed equals 0? And I'm going to let my bx cubed this time be opposite of 1 minus x, which is x minus 1. So from this, I get the equation bx cubed minus x plus 1 equals 0. So here I have another equation, just like I had here. Up here, I have a quadratic equation. Down here, I have a third degree. Okay, and so on, right? We can do that, etc., etc. If you want, you can let b, well, let's choose another one this time, because I use a, b. Let's go c. Wouldn't cx to 1,000 minus x plus 1 equals 0 here? But then again, these are all exceeding the degree of the polynomial, right? If I have, again, when I put it back here, it was the following in the end. We said, otherwise the left side would be non-zero with infinitely many roots, and these have, we're talking about the many roots that I'm talking about. Here's one root. You know, you can solve for that, you get a root. Solve for this one, you get another root, another root. So that's what that means. Okay. Now, so how do we test? Let me go back to the page of the book. I'm going to change my share and go back to the book. Let's take a look at this one. Now, how do we test for linear independence or dependence? There you go. So this is the test now for linear independence and dependence. So suppose we have, again, a set of vectors in the vector space. So to determine whether the set of vectors is linearly independent or dependent, then we got to follow the steps. Form the vector equation, which I did in all my examples I've done. This is what we did. Form the vector equation. and write a system of linear equation in variable C1 to Ck. Use Gaussian elimination to determine system has a unique solution. If the system has only trivial solution, then it is linearly independent. If the system has also has non-trivial solution, then it's dependent. Remember, homogeneous system will definitely have trivial solutions. So this is true for this part is true for every homogeneous system. However, if the system also has, to be linearly dependent, it must have non-trivial solutions. Okay. All righty. Now, let's take a look at another example here. So I'm going to change my share, go back to my notepad. All right. Now, for this example, next example we're going to look at is the following. We are in section 4.4. Okay, so for this example, to kind of go to that polynomial example I had, let's say I want to answer the following, or let's say this time I have a first degree polynomial that is 1 minus x, and the second degree polynomial that is 5 plus 3x minus 2x squared, and P3 is 1 plus 3x minus x squared. Okay, so we want to know, are these linearly dependent? Is this set linearly dependent or independent in P3 in the set of all, or actually let's make that P2 in P2. Okay, so let's do the linear combination C1 P1 C2 P2 plus linear combination C3 P3 equals 0. Let's solve this one. And when you solve this one, you get C1, 1 minus x, plus C2, 5 plus 3x minus 2x squared, plus C3, 1 plus 3x minus x squared equals 0. Okay. Now, let's combine like terms here. So C1 plus 5 C2 plus C3. That's the coefficient, C1, 5, and C5, C2, and C3. Plus, the second term is going to be negative C1 plus 3C2 plus 3C3 times x. And the last one is going to be what? This is the coefficient on x squared now. So they are negative 2C2, negative C3x to the second equals 0. Okay. In the system, this is the matrix of the coefficients only. This one is, but if I set it as a system now, the coefficient constant should be 0. This one should be 0, and this one should be 0 because there's no x term. There you go. On this other side, you can write, if you want, plus 0x plus 0x squared. So the coefficient, the constant must be 0. The coefficient on x must be 0. The coefficient on x squared must be 0. That's why. And then the middle one is negative C1 plus 3C2 plus 3C3 is this time 0. And of course, negative 2C2, negative C3 equals 0. So I have this matrix. Now, for this one, again, you can do Gauss-Jordan. Let me show you both. I did determinant of A. Determinant of A ended up being 0. Okay. So if determinant is 0 again, because this is homogeneous system, so we don't say there's no solution. If determinant is 0, could be, but not for homogeneous. The other aspect of determinant 0 was it has infinite solutions. And infinite solutions means that the system has non-trivial solutions. In other words, 0, 0, 0 is the only way this could be 0. and therefore it is a dependent system. If you go through Gauss-Jordan, which I did, by the way, through, again, I use a software, I get 1, 0, 0, 0, 1, 0, and negative 3 halves, a half, and 0. And again, you see a row of zeros. And for this one, you can try this. I let C3 equal T. My free variable is C3, and my parametric solution is going to be 3 halves T, negative 1 half T, and of course, T itself. So this means, again, the same conclusion. It has non-trivial solutions. This system has non-trivial solutions. So however you look at it, the system is dependent. Again, what does that mean? That means you can write these, one of these as a linear combination of the other. Okay, you can write any one of them as a linear combination of the other two. Okay, now geometrically, by the way, how do we recognize linear dependence or independence? So, for example, let's say we're done with this one. Now we're talking about the geometric interpretation of dependence or independence. So let's talk about linear dependence. Linear dependence. So geometrically, what does this thing look like? Well, suppose I have two vectors that are collinear. This is my V1, this is V2. Okay, and of course, vectors. So you can boldface them. I don't want to put arrows on them because then they will interfere with the arrows up there. So you have two linear vectors, two collinear vectors, and there you go. Just throw in our X, Y, Z in there. There. So that's an example of linearly dependent vectors in R3. Of course, the vectors could be in the other direction, right? Let's say I have E3 here. Any two of these would work. So if they're collinear going in the same direction, collinear going in the opposite direction. Or, well, let's say I have a plane. So I have this plane, and suppose I have, this is a vector V2 and another vector V1, and I have this vector V3. Again, the key, folks, the key is that these are on the same plane, okay? Now I'm going to make this plane go through, there you go, X, Y, and Z. So now again, I'm looking at R3. As long as all three vectors are on the same plane running through the origin, then this set of vectors are dependent because they lie on the same plane. So really all you need is R2 to explain these, not R3. True? Because they lie on that plane. Okay. Or now they could be, let's say, same plane. I'm going to draw it here now in R3 again, I'm thinking. This is the Y part. They could look like this. For example, two of them could be collinear, right? Two are collinear, and the third one still on the plane, cannot get out of the plane. So here is the other possibility. So these are all example of dependent vectors. Okay, all of these, one could be written as a linear combination of the other one. Now, what does a linear independence look like? And geometrically, well, so let's say I have one vector, V1 going here, vector V2, a second vector, V2. I did put arrow on it just to have it in mind. So I have two vectors here, right? And there you go. Here's X, Y, and Z. So they lie on different planes, actually, through the origin. There you go. The origin is the key here, by the way, folks, because remember, 0 The set must be non-empty means the vector 0, 0 has to be there. So all of these are through the origin. Okay, so this would be linearly independent, right? Now, the other way it could be linearly independent, let's look at something like this one. So I could create that plane again. And suppose here, I'm going to make V2 and V3 to be coplanar, means they're on the same plane. So here is V1 and here is V2. So I've got these two coplanar vectors. Now the other one, boom, V3. It's not on that plane, it's somewhere else. So this is okay. Here's Z, here's X, and there is Y. So these are just illustrations. Again, V3 here is not on the same plane as V1, V2. All right, so hopefully that helps kind of visualize what we mean here. Now, we are almost done. Section 4, I'm sorry, let's look at our last work here. So I'm going to switch back to the page of the book. And let's go to Theorem 4.8. In Theorem 4.8, now this is a property of linearly dependent sets. And I've been referring to this as I've been doing this lecture all along, but now this formalizes it. If a set that has at least two vectors in it, that set is linearly independent if and only if at least one of the vectors in the set can be written as a linear combination of the others. So that's what we mean by dependence. And by the way, ideally, we would like to have independent sets, right? Why would I want to duplicate? Because linearly dependent sets duplicate vectors, right? If I can write vector 3 as a linear combination of vector 1, vector 2, then I really don't need linear vector 3, right? If vector 5 could be written as a linear combination of vectors 1, 2, 3, I don't need vector 5. It's just redundant, right? Because V1, V2, V3 will do the same job for me. So that's the reason. Now, so let's take again, if you want, the proof is in there, by the way. The key is that, there you go. When these are linearly dependent, that's right in here. See that vector V1 can be written as some combination scalar multiple of the others. The C2, C1 is a scalar multiple. C3 divided by C1, scalar multiple, as combination of the others. Okay, so again, the proof is there for those that are interested. And now there is a corollary to this theorem. And this is interesting remark. The zero vector is always a scalar multiple of another vector. So because C is zero, right? For zero vector, I'm sorry, C is not zero. For a zero vector, C could be 1,000. 1,000 times zero is zero. So zero vector is always a constant multiple of another vector. Okay, and let's see. So for the corollary, let's say you have two vectors in a vector space. These are linearly independent if and only if one is a scalar multiple of the other. Again, the set is linearly dependent. Means you can kind of interpret this as like one vector depends on the other kind of thing. In that sense, they're dependent. If and only if one is a scalar multiple of the other. Okay. Now, and there you have that one. And we get to the exercises, which is good. So for these exercises, now let's see. Let's take a look at, we're going to take a look at some even number exercises here. Okay, so let me choose some of these. And hold on. Oops, sorry, I didn't mean to pause my share. I was on the book and we're going to share it. Hold on. Sorry about this. Okay, and again, I want to make sure that my screen, here I'm sharing the screen with you. Hold on, resume. Okay. Again, this Zoom thing, still, as since we've been on Zoom for at least 5 years, I'm still having trouble with Zoom. Okay, let's take a look at, I'm going to do exercise number 6 here. So in number 6, you're given two matrices. These are elements of the set of all 2 by 2 square matrices, 2 by 2. We want to determine whether the given matrix in number 6, this is the given matrix. Is this a linear combination of A and B? So let's take a look at this one. And after number 6, by the way, we're going to do number 12. We're going to look at the spanning sets. But first, let's take a look at number 6. Can I write this matrix as a linear combination of the other two? So we're going to change my share now. And so here we go. I've written the matrix down and let's try it. So if I can do this, that means I can write the matrix 6, 2, 9, 11. Okay, equal to a constant multiple of matrix A plus constant multiple of as the sum of the scalar multiples of the other two matrices. So, and remember for matrices to be equal here, all the elements in the same row column, same row, same column must be the same, okay? So in other words, C1A here, that means C1 times each of these, right? So I have 2C1, negative 3C1, 4C1, C1. That's what C1A means. What does C2B means? That means C2 times each of these. That's 0, 5C2, C2, negative 2C2, right? Those. So the sum of 2C1 and 0 must be 6. So I can write my system now. 2C1 equals 6. So from this right away, I get C1 is 3. True. If 2C1 is 6, then C1 must be 3. Now, this element in the first row, second column, right? First row, second column. What do I have? I have negative 3, right? Negative 3C1 and plus 5C2. That should equal to 2. True. And the next one is 4C1 plus C2 is equal to 9. And C1, the last one, is C1 minus 2C2 is equal to 11. So here's my system, okay? And there we have this one. So hopefully everyone follows now how I'm getting these numbers, right? Okay. And let me real quick go back just to make sure I copied the right problem here. Yeah. A is, because the plus minuses make a big difference, don't they? So I'm just checking to see. Yeah, I did copy this correctly. I'm good. Never hurts to check. Cool. Now I need to solve the system, right? So notice first equation says C1 is 3. Now let's solve, if I have C1, let's solve for C2. So for example, in here, C2 is 9 minus 4C1, correct? So that means 9 minus 4 times 3. 12, 9 minus 12 is negative 3. So C2 is negative 3. Well, let's take a look at the last equation. C1 is equal to 11 plus 2C2. Well, C1 is 3, right? 3 equals 11 plus 2C2. So from this, 2C2 must be negative 8. Subtract 11, divide by 2, and I get negative 4. Now, C2, we just said is -3, but then it turns out to be -4 in another equation, correct? So that means the system is inconsistent. Inconsistent system. That means pretty much it has no solution, right? Inconsistent system has no solution. Therefore, this I cannot write the matrix 6, 2, 9, 11. I cannot write it as a linear combination of A and B, of A and B, those two matrices of A and B. All right, now let's take a look at, for instance, let's look at another one. How about, let me switch, share the book. And this time, let's take a look at how about number 12? In number 12, we can look at a couple of these. In number 12, and then we'll do maybe number 16, something similar to your homework problems. In this segment, determine whether the set S spans R2. Remember, spanning set. That means every vector in R2 has a representation or can be written as linear combination of the vectors that you see. For instance, in number 12, every vector in R2 can be written as a linear combination of those two. We'll see whether we can do this or not. If the set does not span R2, that means if you cannot write every vector in R2 using this set, then give a geometric description of the subspace that it does span. Okay, that's the case if it doesn't span R2. Okay, so let's check it out. We go to my notepad. Okay, so we're doing exercise number 12 now. In exercise number 12, the set is S, and it's got only two vectors, 2, 0, 1. Can every vector you can imagine in R2 be written in this as combination of only these two? Well, so I'm going to let a vector U be U1, U2. This is like a typical vector. Let this be any vector in R2. Okay, so we have any vector in R2. Now, C1 times V1, remember that's 2, 0, plus C2 times the second vector in S is 0, 1, right? This should equal to all vectors in the form xy, U1, U2, scalars. So that means 2C1 is equal to U1 and C2 is equal to U2. Therefore, now this one has a unique solution. True, it has a unique solution. And why? Because if you look at, for example, let's look at the determinant of the coefficient matrix 2, 0, 0, 1. What am I getting 2, 0, 0, 1? Well, the coefficients here are 2C1. There's no C2 in the first equation, right? There's no 2C. There's no, I have C1, no C2. So it's 2, 0. And the second equation has no C1, it's 0. The coefficient on C2 is 1. So there you go. That's what I'm talking about, this one. And the determinant of this matrix is going to be what? It's going to be 2 times 1 minus 0 is 2, which is not 0. True, so determinant of A is not 0. Because, so that's how we know it has a unique solution. If determinant is not 0, that means the matrix is invertible, and invertible matrices have solutions. Okay, so this tells me has a unique solution. The determinant of the coefficient matrix again is non-zero, and therefore, so we can say that this set actually spans R2. Yes, spans R2. Any vector you desire can be written as a combination of these two. And here's how, again, if you solve this one, right, for this one, C2 is U. I mean, we're looking at the solution. Let C1 be first component divided by 2. Let C2 be just the second component there. So for instance, let's say, how about this vector? I'm going to choose vector example. Let's say vector, I don't know, 5 and negative 20. There, that's my vector. Can I write it as a linear combination of these two? Well, according to this, it says let C1 be the first component, 5/2. C2 be exactly the number that I'm thinking of, negative 20. Now let's do this. C1, that's 5/2 times 2, 0, plus C2 is negative 20. Negative 20 times 0, 1. Let's see, what do we get? So 5/2 times 2 is 5, plus, now this is in the, what do you call it? The linear combination. Let's go comma, because I'm thinking of a vector here. Okay, and negative 2 times this one gives you, oh, actually, you know what? This should work, no problem. Because I'm doing a vector. I don't need to double vector that. Sorry. So let's do it again. 5/2 times 2, 0 is 5, 0. Plus negative 20, 0, 1 is 0, negative 20. See, I'm adding two vectors. First components, 5 plus 0. Second components, negative 20. And that's exactly what this is. Okay, so there you go. That worked. All right. Sorry about that. And so this was exercise number 12. Let me tidy up this one, not to confuse anyone. All righty. And this was indeed a plus. Okay, let's take a look at another exercise. In another exercise, let's see. Let's take a look at, let me go back here and change my share. I said we're gonna look at number 16 also. Yeah, let's do number 16 to be different. All right, in exercise number 16, I'm gonna write it down in exercise number 16, section 4.4, number 16. Exercise number 16, here S is equal to, the vectors are 1, 2, comma, negative 2, negative 4, comma, a half 1. Now remember, we're working with R2 and we're given 3 vectors. Really in R2, we need 2 vectors, right? So let's see if this spans it. So let me switch to my note here, and I'm going to change my share. So for this one, we're going to say, let's see, only vectors of the form, let's say one of them, a constant multiple of 1, 2, are in span of S. Okay, so for example, what do I mean by that? For example, 0, 1. 0, 1 is not in the span of S, right? So, so remember, if these span R2, that means every vector, well, 0, 1 is not in that span. And why do I write T1, 2? Because the way the author made this problem, if you look at the second vector, isn't that negative 2 times first one, negative 2 times second component? This one, you divide 1 by 2, you divide 2 by 2, you get that. So this is really, these two are constant multiples of the first one. So In this set, all the vectors are just constant t multiple of 1, 2. So how can this span every other vector? So for example, if I'm thinking of 10 and 17, 10 and 17, it's not going to be in the span either. That means I cannot do t times 1, t equal 10, and well, let's see, this one actually may work, but the key is the one with 0. The 0 ones doesn't work. So yeah, never mind this one. We just need one example. So it doesn't span because 0, 1 is in there. And also 1, 0 would not be there, right? It's not in the span of S because it's the same number t. If t is 0, then both of these become 0. 0, 0 is there, but not when one or the other is 0. So for example, 7, 0 is not in the span. Okay. But the other ones you could make it to where it is. Okay, so number 16, we got that one. Let's take a look at a different one. I'm gonna take a look at let's do example of spanning sets. See, 20 all the way up to there. So how about number 24? In number 24, determine whether the set spans R3. If it doesn't span R3, then give a geometric description of what it does span. Okay. Description of the subspace that it does span. So let's take a look at number 24. Okay. In number 24, the set S is given by 101, 110, and 011. Okay. Let me change to my document. Okay, so for this one now, again, I'm going to write the linear combination. We're going to do C1, V1 plus C2, V2 plus C3, V3 equals U. Oh, now because it's spanning the same, by the way, it's the set of these, the subscript actually, it's got to be the same constant. Okay, we're gonna, no, it's actually, we can make it different. Never mind. So there you go. That's just general form of it. U here is any vector. There you go. U is an arbitrary vector in R3. So any vector you want to make up. So let's keep it with the subscript that's C1, C2, and so forth. Okay, so let's see. C1, now the coefficient, C1, C2, 0, C3. So that's C1 plus C2 should equal the component of U. Remember, U is made up of scalars, U1, U2, U3, right? This is any vector in R3. So the first component, U1, is the sum of the first components of vectors in S. The second component should be C2 plus C3, that's U2. And the last one, C1 plus C3, is in U3. Okay, now this one, the determinant of, call this matrix A of the coefficient matrix A. That would be the determinant of 101, 101, 110, and 011. And this determinant doesn't equal to 0. Okay, that determinant doesn't equal to 0. And so therefore, system has a unique solution. Okay, so the system has a unique solution. That means S, again, spans R3. In other words, every vector that you make up, we'll be able to write it as a linear combination of these. Okay. Now, this determinant, again, it's not 0 because I tried it. A quick way you can do this one to see what the determinant is I'm sure we've seen it, we talked about it. Repeat the first two columns. And look at product going in this direction. That's 1 in this direction, plus 1 plus 0. So it's going to be 2 minus the product going in this direction, diagonal, off diagonals. 1, 0, 1 is 0. 1, 1, 0 is 0. 0, 1, 1 is 0 minus 2. See, determinant is not 0. Determinant of A is 2. So that's what I was referring to. Okay, so we got that one. And let's see. Let's take a look at maybe that's pretty much all the rest of these. I wonder if you could stop now. The rest of these are the same thing. Test for linear independence. No. Again, for these, you would do them the same way. For linear independence, remember, if the determinant is 0, that means the system is linearly dependent. If determinant is 0, linearly dependent. Determinant not 0, linearly independent. So for all of these, you just set up the system just like I did in my number 24 exercise. Let's see. For instance, I want to see if there's other ones. Okay, let's take a look at number 42 actually. So I'm writing down number 42 here. First, the set is made up of polynomials. The first component, x squared minus 1, second one, 2x plus 5. The question, determine whether the set of vectors in P2 is linearly independent or linearly dependent. We're doing number 42. So switch to number 42 now. Okay. So for number 42 here, I'm going to go again C1, x2 minus 1. This is how you work almost all of these in this section, 2x plus 5. Write the vector times the scalar multiple, set it equal to the 0 vector on the other side, however it looks like. Because we're talking about P2 here, so we're looking at the 0 vector in P2. Equate the coefficient, you get negative C1 plus 5C2 constant. Okay, negative C1, 5C2. That should equal to the 0 constant on the other side. The x term is 2. 2x, 2C2 is the x term here is 0. And the first terms, the squared term is C1x squared. So that means C1 is equal to 0. Well, from this, we get C1 is 0. From this, we get C2 is 0. And up here, of course, 0 plus 0 is 0. Well, the solution set is what? This 0, 0, isn't it? Right? So this thing, this system has trivial solutions only. Trivial solution only. So what does that mean? If it has trivial solution, therefore set is linearly independent. So trivial solution, the set is independent, otherwise it's not. Okay. And let's finish this one. I'm going to do one last one, folks. I know you're probably getting tired of this. I know I am. Let's take a look at something from ladder part. How about something in this segment, showing linear dependence again? Let's do, I don't know, number 52, this one. This one looks good, right? Number 52. Let's try this one. So the question, show the set is linearly dependent by finding a non-trivial linear combination of vectors in the set whose sum is 0 vectors. See, remember the key is to find non-trivial solution to this homogeneous system. So I'm going to write down number 52 in here. So we're in, again, section 4.4, exercise number 52. Number 52, the set of vectors 1, 2, 3, 4. So it looks like they're looking at R4 here, right? 1, 2, 3, 4, 1, 0, 1, 2, and 1, 4, 5, 6. Okay, so that's number 52. Let me share with you again. There you go. So I just wrote that one down. So what do I need to do? Just like before again, we need to write the vectors in S as a linear combination of C1, V1, C2, V2, plus C3, V3 equal to the zero vector. Now the zero vector in R4, right? The zero vector in R4 looks like this, 0, 0, 0, 0, right? Okay, and here we go. We're gonna add up all the first components, right? C1, C2, C3, like that. C1 plus C2 plus C3 equal this first 0, 0. And then the next one, 2C1, 0C, oh, I'm sorry, 2C2, 0C2, 4C2. So that makes it 2C1 plus, or C3, sorry, I said 4C2, 4C3. That should be 0. The next one, 3C1, 3C3. Got C1, C2, C3 like that. 3C1 plus 1C2 plus 5C3. That's what that one is. 3C1 plus C2 plus 5C3 equals 0. And finally, the last one is 4C1, 2C2, 6C3. I left the C1 out of this one because I'm thinking, talking, writing, and doing everything at once. That's why. So 4C1 plus 2C2 plus 6C3, that should be 0. Okay. So let's do this one. Now, first, the matrix is going to be 1, 2, 3, 4, right? 1, 2, 3, 4, first column. Then next column is going to be 1, 0, 1, 2. The next column after that is going to be what? 1, 4, 5, 6. This one. And so for this one, once you go to Gauss-Jordan, okay, let me just say you go Gauss-Jordan on this one. It's going to look like this. It's going to go 1, 0, 0, 0. Again, I've done this one using symbol app. And I have 1, negative 1, 0, 0. And we have 2 rows of zeros now, right? So that clearly shows that there are dependencies in here. Otherwise, if you get 4 independent equations, this wouldn't happen. Now, of course, with 3 unknowns, I have 4 equations, so I know this is not going to be independent, that is, sorry. Because you got too many equations. I only need 3. There's 3 variables. I only need 3 independent equations. Why do I need 4, 5, 6, 7? That just shows dependencies among these vectors. Okay, and so when we solve this now, remember, these are the coefficients on C1, C2, C3, and on the other side of here, the augmented matrix, you have 0, 0, 0. So I'm going to let the free variable be C3 here. Okay, C3. That means that's T. Now, C2 is in terms of C3. Move C3 to the other side. So C2 is equal to C3. That means C2 is also T. C1, take C2, C3 to the other side. So C1 is negative C2 minus C3. But then C2, C3 are T, correct? So it's going to be negative T, negative 2T. That's what that one is. Perfect. So we have the parametric solutions. It's going to be negative 2, 1, 1. There you go. Which sometimes I write it as a row vector instead of a column vector. And there you go. Therefore, the system has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, The system has non-trivial solutions, right? Therefore, the vectors form linearly dependent sets. So we have linearly dependent set. Okay. And you can see, for example, how this can be zero. Let's say if I just go with let t be 1. I'm just going to illustrate how this works. How can I get 0 here? Let t be 1. So one solution is negative 2, 1, 1, right? And again, this is C1, C2, C3. That's one such solution. So I'm going to do negative 2 times the first vector, negative 2 times 1, 2, 3, 4, plus C2. C2 is 1. 1 times 1, 0, 1, 2. Plus C3 is 1 also. 1 times 1, 4, 5, 6. 5 and 6. Now let's do this. Negative 2 times 1, this one, is negative 2 plus 1 plus 1, 0. Negative 2 by 2, negative 4, plus 0 plus 4, 0. Negative 2 times 3, negative 6, plus 1 is negative 5, plus 5 is 0. And finally, negative 2 times 4 is negative 8, right? And this is negative 8. Plus 2 plus 6, that makes it 0. So you have a 0 in 4, in R4. There you go. Okay, so there you have it. Let me stop here. So we are done, by the way. We are done with the entire section. Now we have completely covered section 4.4. And in my next video, next lecture, we're going to talk about basis and dimension. So I'm going to stop this one. And again, thank you for watching, everyone. And what you called it. So we'll see you in another video, I hope. Hope to have you in another video. Thank you.